Okay, linearization and Newton's method. We're actually only going to be talking about linearization today, and Newton's method is actually a topic that is on the BC AP Calc test, not the AB one, which is the one that we're taking. So, 4-5, we have some quick review questions here that I, again, will just leave on the PowerPoint for you, and then the solutions are here. What we're going to be learning about. So, linear approximation, differentials, estimating change with differentials, and absolute relative and percent change. We won't talk a lot about the absolute relative and percent change. But linear approximation, engineering and science depend on approximation in most practical applications. It's important to understand how approximation techniques work. And once you kind of get the hang of it, it is kind of a neat little trick if you don't have a calculator, or even just to see how mathematicians found approximate answers without calculators way back when they had these crazy complicated functions. If they could find the equation of the tangent line, then they could approximate the value of the function using the tangent line. So it was a pretty neat little trick. Linearization. If f is differentiable at x equals a, then the equation of the tangent line, L of x equals f of a plus f prime of a times x minus a, defines the linearization of f at a. The approximation, f of x, is approximately equal to L of x, is the standard linear approximation of f at a. The point, x equals a, is the center of approximation. So we have here, what I want you to really see is that this equation, L of x equals f of a plus f prime of a times x minus a, is actually just the equation of the tangent line, y minus y equals m times x minus x, where your L of x is your first y, f of a is just my second y, it's just subtracted to the other side, or added to the other side, plus f prime of a, well, that's slope, right, times x minus a, which is my first x and then my second x is a. My second y would be f of a. So I want you to really understand that linearization is just finding the equation of the tangent line. So that is, no, never mind. Okay, so what we have here is this equation of a parabola, y equals x squared, and this purple dot right here is a. That is at 1. Okay, now notice we have a gray tangent line going through that purple dot. Don't worry too much about these dots up here. I'll explain what they are here in a second. But what I can do with this applet is I can move this purple dot back and forth. So right now, I'm going to continue to make that 1. All right? Now, these dots up here represent the value of the function at 1.5 and the value of the tangent line. And you can see that if I put 1.5 into my function, I get 2.25. If I put 1.5 into the equation of my tangent line, I get 2. Now, notice as I slide this bar and make those points go closer to A, notice how the values here get very, very close to each other. The error is very small. As I keep getting closer and closer and closer to A, notice how my error is getting smaller and smaller and smaller, which basically just means that the change between those two values is becoming very, very, very minuscule. Okay? Now, as I move away, notice that the tangent line value and the function value, again, are growing very far apart, and my error is getting larger. See there, I have a 73% or 74% error. But as I move this point back to that center of approximation right here, I have a very, very small error. And so what mathematicians did way back when is, if they at least could come up with the equation of the tangent line at a certain point, they could put in points very close to that a value, and instead of putting them into the function, they could put them into the tangent line and get a very, very close approximation. Now, notice that as I move farther and farther away, my error gets larger, and I can't really use that tangent line. But if I wanted to come up with at 1.55 what the value of my function was, if I came up with a new tangent line that was closer, then I could come up with it being about 2.4 by putting it into the tangent line that got closer to 1.5. So the biggest idea here is to remember that if I have a tangent line, then I can put values in my tangent line to get my answers instead of this more complex function to get answers, as long as my tangent line is going close, is very close to that place where I want to find the answer. All right, moving on. Let's get rid of him. An example of finding a linearization, we have the question says to find the linearization of f of x at equaling cosine of x at x equals pi over 2 and use it to approximate cosine of 1.75 without using a calculator. Now, what we have here is we need to recognize that pi over 2 is actually 1.7 something, okay? Notice that it's very similar or very close to the value 1.75. So that's why pi over 2 is going to be our center of approximation, because it's close by to 1.75. Now, since f of pi over 2 is 0, when I put 0 in, or pi over 2 into cosine, I get 0. Our center of approximation, or our point of tangency, is pi over 2, 0. And you can see that that place on the graph is down here, pi over 2, 0. The slope of the tangent line would be f prime of pi over 2, which would be obviously the derivative, which is negative sine of pi over 2, which is negative 1. And if I put this tangent line in, you should be able to see that the tangent line is negative 1, the slope of it. Therefore, the linearization, which is just the equation of the tangent line, is y minus, my y value is 0, plus m, that's my slope, negative 1, the derivative, times x minus my x value, which is pi over 2. And I could simplify that to say that that's negative x plus pi over 2. Since the tangent line is now, we found that, instead of putting 1.75 into my original function, which I would have to use a calculator or some other method to come up with the answer, I can instead just put 1.75 into my equation of the tangent line and get a very close approximation of that answer. And so my answer would be negative 1.75 plus pi over 2. And that's as far as we would go without a calculator. So now we're going to visit our friend with the bow tie, and he's going to go over a couple other examples with you.
Let's try an example of this. So A, find the linearization, capital L of x, of f of x at x equals a. Then answer, how accurate is the approximation, capital L of a plus 0.1 equaling f of a plus 0.1. The function f of x is equal to x plus 1 over x. And remember, that's for a equals 1. So what we're going to do here is plug this into the formula, and that means that we need to take the equation and find its derivative. So we have f of x equals x plus 1 over x. F prime of x is going to equal, well, the derivative of x is just 1, and the derivative of 1 over x is negative 1 over x squared. So we need to find two things. We need to find f of 1, and we need to find f prime of 1. Let me do f prime since it's set up for me. That's equal to 1 minus 1 over 1 squared. So it's 1 minus 1, which is 0. Let's take and find f of 1. F of 1 is going to be equal to 1 plus 1 over 1, which is 1 plus 1, or in other words, 2. Now we need to find the actual linearization, capital L of x. We have all the information we need to plug into that. So we have L of x is equal to, and we have to do f of a, which is f of 1, and we said that f of 1 was equal to 2. Then plus f prime of a, which is f prime of 1, which we said was equal to 0. Then times x minus a is 1, so it's x minus 1. And then that, of course, is equal to 2. So our approximation, L of x, is equal to 2. Part B was to determine how accurate the approximation for L of a plus 0.1, which is L of 1 plus 0.1, in other words, L of 1.1. So L of 1.1, well, it actually doesn't matter because we found that L was a constant term, so that means that it's equal to the 2 that we discovered over here. We want to compare that to F of 1.1. And when you plug that into the original problem, which, remember, is up here, we plug in 1.1 and 1.1. When you work all of that out, it equals 2.009. And what that means is that it's off by a little bit, but it's off by less than 1/100th, which is pretty accurate in terms of looking at what we have here.
Okay, differentials. Let y equals f of x be a differentiable function. The differential dx is an independent variable. The differential dy is dy equals f prime of x dx. There are a couple things I want you to really understand in this definition. We should all recognize that the derivative is equal to dy over dx. Okay? And we also understand that dy refers to the change in y values over dx, which refers to the change in x values, which gets us to where we have a tangent slope line. Okay? So that is the derivative dy dx. If I would just simply solve this for dy, all I'm doing would just multiply over my dx. So dy is equal to f prime of x dx. All I have done is I've solved for dy. I've just multiplied dx over to the other side. So we have just written the derivative differently. We've just solved it for dy instead of leaving it in the form of dy dx. The differentials are dx and dy. The independent differential is dx. The dependent differential is then dy because it depends on dx. So let's talk about what the differential dy really means. So we are to find the differential dy and evaluate it for the given value of x and dx. And we have this particular function, y equals x to the fifth plus 2x. We're talking about at the place x equals 1, and we're talking about x changing, dx, the change in x's, x changing by 0.01. And what we're going to do is figure out if x changes by 0.01, what is y going to change by at that place x equals 1. So to find dy, we're just finding the derivative. dy dx would be 5x to the fourth plus 2. That's the derivative of y. But all I'm going to do is then just multiply my dx to the other side. Now if I put in my values, x equals 1 in for x and 0.01 in for dx, what we have found in the end is that dy is equal to 0.07. And all that means is that if x changes by 0.01 at 1, then y is going to change by 0.07. So I have a graph here for us to see. I put in the graph x to the fifth plus 2x right here. That is this function in the black. And then I put on there the 0.13. That is the 0.1 f of 1. Let's zoom in a little bit here. And I also put in a tangent line. So the tangent line right here is 7x minus 4. And that is in the purple, if you can see that. Okay? Now, I put point A on there as 1, 3. So that's what I would get if I put 1 into my function. I would get 1 to the fifth plus 2 times 1, which is 3. Okay? So that's the point A down here. Now what I've done is I've put on the point 1.01, because remember we have said that x changed by 0.01. What we will see is that y will change by 0.07. Okay? So all I did was I put 0.01 into my function and I'd get 3.07. So differentials just tell us that if x changes by a certain amount, then dy or y will change by another amount based on the derivative. Let f of x be differentiable at x equals a. The approximate change in the value of f when x changes from a to a plus dx is df equals f prime of a dx, which is exactly the same thing as what we were just talking about. All that is saying is that if x changes by this dx value right here, then y is going to change by just solving for dy. I'm going to put, or df, they say the same thing, by putting dx on the other side and multiplying it by my derivative. And it gives me the approximate change in the value. Examples estimating change with differentials. The radius of a circle increases from x equals a 5 meters to 5.1 meters. The radius of a circle changes from 5 to 5.1 meters. We're going to use the derivative to estimate the increase in the circle's area, or how is that going to change the area of the circle if the radius changes that 0.1 meter. So we have a relationship between the area of a circle and the radius. Area equals pi r squared, and so we can easily come up with the derivative. dA dr would be 2 pi r. All I'm doing is then just moving my dr to the other side, so the differential dA is equal to the derivative 2 pi r times the differential dr. Now, we should all hopefully see that the change, or dr, is going to be 0.1. That's what our radius is changing from 0 to 5 to 5.1 would be a change of 0.1. If I put 5 into my radius, and I put 0.1 into my dr, then I will get pi meters squared. So what we are saying, or 3.14, what we are saying is that if my radius changes from 5 to 5.1, then that's going to affect my area by pi meters squared. It's just going to make it pi meters squared bigger than what it was at 5 meters.
See it clearly illustrated. Let's take and say that we want to find dy and then evaluate dy for the given value of x and dx. And the equation that we're going to do this, or the function that we're going to use, is y equals x squared times log x, where x is equal to 1 and dx is equal to 0.01. So the first thing we want to do here is to calculate its derivative. So the first derivative of x squared log x means we have to use the product rule because we're multiplying two functions. So we take the first function times the derivative of the second function, and then add to that the second function times the derivative of the first function. So this is my dy dx, my y prime. According to the formula that we just looked at, dy is equal to the derivative times dx. So what I would have is x, of course we can simplify that to x times dx plus, and I'm going to rearrange these so there's no confusion, 2x times log x times dx. Now I can evaluate my dy because I have all of the information I need given to me. X is 1 and dx is 100th. So dy is equal to 1 times, actually let me put that in parentheses, 1 times 100th plus 2 times 1 times the log of 1 times, and I'll put that in parentheses, the 100th. And when we work all of that out, remember that the log of 1 is equal to 0, which means this entire term is 0. So dy will equal 1 times 0.01, which of course is just 1/100th. We often use differentials to estimate change. There are 3 types of changes that we can find. So let's take a look at each one of them. First of all, we're called absolute, relative, and percent change. Let's look at absolute first. Absolute says that the true amount of change is the delta f of x equals f of a plus delta x minus f of a. But we can estimate that change by using df equals f prime of a times dx. So that will be an estimation of the true change. So that's absolute change. Let's take a look now at relative and percent change. My setup is a little bit different. I have relative change and I have my true change and my estimated change. So for relative, the true change is delta f of x divided by f of a. And the estimated change for that is df over f of a. So df divided by f of a. For percent change, all you'll notice is that you multiply both of the relative changes by 100. And that's the relationship between the relative change and the percent change. Let's try an example of this. Let's say that we have the following word problem. In the late 1830s, French physiologist Jean Puiseux discovered the formula we use today to predict how much the radius of a partially clogged artery has to be expanded to restore normal flow. His formula, V equals K times R to the 4th power, says that the volume V of a fluid flowing through a small pipe or tube in a unit of time at a fixed pressure is a constant, K, times the 4th power of the tube's radius, R. The question is, how will a 10% increase in R affect V? Well, remember, changes are with respect to our first derivatives, and so that's what we'll use in this problem. So let's take V is equal to K times R to the 4th and work with that. What we know is that the derivative of V with respect to R is going to be equal to 4K times R cubed. So that's my derivative of the volume with respect to R. Now, what I'm interested in here is that we have dV, which is equal then to 4K R cubed times dr. All right, so we're interested in that dV. Now what I want is, how does that change in the volume affect the overall volume? So dV divided by V. So that's going to be equal to my 4K R cubed times dr over the original volume, which is K times R to the 4th. So what we see here is that the K's cancel, and in terms of the R's, the entire R will cancel out all but one of the R's in the denominator. So that my answer will be equal to 4 over R N times dr. And what that means is that we will get a change of 4 times the change of R, and that means that a 10% change will actually produce a 40%, 4 times as much, 40% increase in the flow. All right, well, now it's time for you to try a problem. And the problem that I would like you to do is this. Minting coins. A manufacturer contracts to mint coins for the federal government. The coins must weigh